Thank you, Ashwin. And then I'd like to thank the organizers, Ashwin, Nati, and Mike, for this great opportunity. I'm glad to see many friends as well as many new faces as well. So today I want to talk about something called the higher very phase. And then this is going to be very short, quick introduction. Um, so it is some sort of a many-body version of very phase. I think you may have heard about very phase, of course, many times in condensed matter physics. So the higher very phase is some sort of generalization. Um, and in fact, in my presentation, I'll be using the language and techniques from tensor networks. And so I think this morning, Ignacio gave a great introduction to the tensor network in general. So a part of my talk will overlap with this morning lecture, although I may be perhaps a bit of prefetching the content from the tomorrow's morning as well. But anyway, I hope it's complementary. And then if time permits, I will also discuss higher dimensions, mainly two spatial dimensions. Okay, so I'd like to begin by acknowledging my collaborator. So Shuhei is the main person who really did all works. And then I learned quite a lot from him. So the content of today is basically much of it from my collaboration with Shuhei. I would like to also acknowledge other people here, Boe, Yuya, Yuhan, Raman, and Jonah, because some part of my talk is closely related to the concept of multi-party entanglement in many-body physics. So there's some related works along this line. Okay, so let me start by just reviewing the regular Berry phase. So it's a quantum mechanical phase in quantum states. Okay, so in a typical setting, we consider quantum state defined in some Hilbert space. And then the state depends on some parameter. It can depend on, for example, the direction of spin as you change the magnetic field adiabatically. Or in solid state applications, sometimes we consider a block state, which depends crystal momentum k, and so on and so forth. But anyway, I just use this symbol, capital X, to represent collectively these parameters. And then as I change this parameter, my quantum state also changes, continuously change. And then typically this parameter it can be considered as a point on some parameter space n, okay? So the question is, as I change my parameter on this parameter space, how does my state changes? Okay, so that is the question. And then the Berry phase is basically the phase acquired by the smooth evolution, adiabatic evolution of this quantum state. For example, I can consider my state along this loop. So my state changes as I change my parameter along this closed loop. So then I go back to the original state physically, because initial point and the final state, they represent the same point, okay? However, the phase of the quantum state is ambiguous, okay? So we may acquire some phase as we have this evolution, adiabatic evolution. Okay, so this is the concept of Berry phase. And then there is the formula that computes the Berry phase. So it is given by the loop integral of this quantity. This is like a first order overlap of two quantum states, one at time t and the other at time t plus dt. And t is the parameterization of the loop, or you can think of this as like a physical time where I'm changing my parameter slowly as a function of time. Okay. And then just to motivate the higher Berry phase later, I want to rewrite it a little bit. Okay, so this part we can rewrite using the partial derivative of this state with respect to the parameter. And then there's this kind of velocity looking term. So this part itself, we call it the Berry connection. Okay. So this part, from the perspective of parameter space, it looks like the coupling of gauge potential, Berry connection, to this loop gamma, which you can think of as like a fictitious particle trajectory. So it's a quantum mechanics setting, but in the end, what we get is it looks like I have a particle trajectory on this space M. And along this trajectory, we can define a particle current. And then this A mu couples to particle current, okay, which is this velocity times some delta function. Okay. So yeah, actually it's written here. So I can think of Berry phase or Berry connection, which is the coupling of particle current along the trajectory to this Berry connection. Okay. And then just like, so it's very similar to electromagnetic U1 gauge field, which couples to the particle current. And then because of the conservation law, there's a gauge invariance. And then the same applies to the Berry phase and the Berry connection. So Berry phase is invariant under the foreign gauge transformation, where we shift gauge connection, Berry connection by the derivative of this gauge function phi, and then the Berry phase stays the same, as it should be, because this gauge transformation is induced by the gauge transformation of the quantum state. Okay. Anyway, this is perhaps something you are already familiar with, and then the idea is we try to generalize. But before discussing Berry phase itself, we also want to discuss a bit of more structure associated with this type of parameterized quantum mechanical system. So we can also consider just the psi of x over entire M. So you can think of this as like a family of state parameterized by x or parameterized over M. And you can ask, is there any topological distinction of such families? Okay. So as it turns out, we can classify such families topologically, and then the proper language to do this is the vector, maybe not a vector bundle, but line bundle or fiber bundles. Okay. So as we just saw, from the quantum state, we can define a gauge field, Berry gauge field, associated to this parameter space. So at each point x on M, we have a gauge connection. So then you can think about classifying such configuration of Berry gauge field, a Berry connection, or we can also think about the curvature of Berry curvature, and then we can think about classifying them. Okay. So it's ultimately related to classifying the states parameterized over M. Okay. So in the following, I'm going to use two different languages. Perhaps they're all equivalent, but at least they look different. So first one is just in terms of the Berry curvature. And then the other one is to use the transition functions or gauge transformations, which relate the wave function in different patches. So let me first mention the viewpoint from the Berry curvature, which is defined here. So starting from the Berry connection, we can consider its curvature, that's the Berry curvature. So that is the two form. Okay. So famously, if you integrate vary curvature over parameter space, let's say two-dimensional parameter space or two-dimensional subspace of parameter space, then you get the quantized integer, that is Chan number, which may appear in many contexts in condensed matter physics. For example, in the quantized Hall effect, we have Hall conductance, Hall conductivity written in terms of a Chan number. Okay. So out of the Berry curvature, we can consider topological invariant, and then the topological invariant classifies topologically distinct parameterized quantum states. Okay, and quantization comes from physicist mind. Quantization comes from the Dirac quantization argument of the magnetic charge. So that guarantees the quantization of this integral, which is a Chan number. Okay. Slightly a bit more maybe abstract way to think about it is to consider this curvature itself, which is a closed and globally defined two form. And then you can sort of state a classification just by using this form. I think here I'm kind of list some math language, which is perhaps not super necessary for the rest of my talk, but this is the language we can use. So this F curvature, or curvature divided by 2 pi times I in my notation, that defines the, that is a member, or that is a class of a particular two-dimensional cohomology class. And then this class is a topological invariant itself. Okay. Okay, but I think in practice it is more useful to consider integral, which is a Chan number. Okay. Anyway, so this is the first perspective in terms of curvature. So this way we can classify parameterized family of quantum states. Okay. Oh yeah, by the way, if you have a question, please interrupt. So here's a second perspective, which should be equivalent to the first perspective, but it looks different. So in physicist literature, this originates from the Wu and Yan's approach to quantum mechanics in the presence of magnetic monopole. Okay. So in this approach, we think about this patching, this manifold M, anticipating that wave function may not be well defined globally. Quantum state itself should be defined globally, but wave function has phase ambiguity. So if we try to make a convenient gauge, we may have to think about patching this parameter space. So that for each patch, within each patch, wave function has a nice smooth gauge. But as I said, it may not continue to hold for the entire manifold. In that case, we can patch. Okay, so this is the case when we have a magnetic monopole, which is living inside, so to speak, the inside of this parameter space. So then there's the kind of difficulty or obstruction to find the smooth gauge everywhere. Okay. But anyway, it is safe to patch this parameter space. Okay. And in this case, we can think about what happens when these two patches intersect, like here and here. So I have a patch U sub alpha, and another patch U beta. They may intersect. In this case, there are two different wave functions, which are physically equivalent, but they may be in a different gauge. Okay, it's also written here. Okay, in the overlap regions, there must be two wave functions, but they must be related to a gauge transformations. Okay, so we call it transition functions, which relate wave functions from different patches. And then in Wu and Yan's approach to magnetic monopole, the non-trivial winding of this transition function is equivalent to the magnetic charge of the monopole. Maybe I can just write it. So we discussed the Chan number, which may be looking like this. So we integrate over parameter space. This is 2 dimensions. but we can patch, so we can integrate, uh, uh, we can split this integral into two regions, let's say m plus and m minus. But when these two patches intersect, a plus, which is the particular gauge choice for the part of m, and then there's another gauge potential m minus, which is for the other part of m, let's call it m minus. They are related by gauge transformations. Okay, so this phi is the transition function I'm talking about. This the integral of the curvature reduces to the integral of this transition function along the intersection of these two patches. And then if I have a non-zero Chan number, this phi has a corresponding integer winding. Okay. Anyway, so this is the alternative point of view for different way of thinking about the topological classifications, and that's related to the previous perspective, like I just described. Okay. Somewhat more abstractly, we can just think about the set of these patches and then transition function relating these two patches. We can think of this as like just data topologically defines this particular fiber bundle, and therefore this classifies the topologically the parameterized family of quantum states. And here's some, once again, kind of math formula for this. But in the end, we get, once again, the second cohomology group. So that's equivalent to the first viewpoint. Okay. So these are kind of well-known formulation for the very phase. And here are some examples. So like I perhaps mentioned in the very beginning, the simplest example could be a question, yes?
The previous example, you talked about the winding number as being equal to the third number. If u alpha intersect u beta is not, it is simply connected, how would you define the winding number?
Yeah, so in that case, there's no winding.
Well, I guess you could always create some patches u alpha and u beta such that all of the intersections individually are simply connected.
Yes, I'm not exactly sure. Yeah, so simply connected, there's no pi 1 is 0, you mean? Yeah. So I think what happens is that if there is obstruction, you cannot find such patch. Yeah. But yeah, so I don't know, it's like a bit of a chicken and the egg problem, but if you can find such patch, since there's no winding possible, Chan number and the winding has to be all 0, in that means you conclude that there was no obstruction. Okay. Other questions? Okay. So I say some examples. So simplest example could be just a 2-level system, spin 1/2. And then as we change the direction of the Zeeman field, yeah, so I didn't write Hamiltonian, but Hamiltonian could be just n dot sigma. And then we consider the let's say the spin down wave function with the energy level comes with plus and minus, and we focus on the negative energy state. And then we can ask how the negative energy state changes as a function of this Zeeman field n. So this is how state changes vertically. In this case, parameter space is a 2-dimensional sphere, thinking about just the Zeeman field with constant lengths, but you can still change the directions. And then there's associated Berry phase for it. So this is the example discussed by Berry. And then this is the perhaps the simplest example. In condensed matter physics, as I mentioned, this parameter can take various different forms. So here's another example, which is a 1-dimensional system but you can go to the momentum space, and then you can find the Bloch Hamiltonian, which depends on one-dimensional momentum. So you can think about this as the parameterized quantum mechanical state with parameter k or kx. You can also add additional parameter by changing the terms in the Hamiltonian adiabatically. So here I just write some one-dimensional Hamiltonian. The details are perhaps not super important, but I can consider these parameters j, small delta, capital delta, and we can consider changing them as a function of time. So in that case, I have a Bloch Hamiltonian, which depends on k, as well as this t, which control these parameters. And then this is a setting of something called Thouless pumping. Okay, so this is the topological invariant associated to the process. Okay, so the corresponding topological invariant is once again Chern number integrated over t and k. So in this case, parameter space is two-dimensional torus, and it can be a non-trivial integer. And in this case, there's the a quantized pumping phenomena. Okay. So this is another example. And then this has been experimentally realized, for example, in this paper. Okay. So all these are perhaps somewhat familiar with for many of you. And then I'm trying to now go to higher Berry phase. So I want to basically generalize this type of quantum mechanical phase to many body quantum systems. Okay, so let me start with, once again, one spin. But if I start thinking about many body physics, I should have many spins. So here's just a kind of picture for one spin, and they have a quantum mechanical overlap, psi at time t and psi at t plus dt, and the overlap represent the Berry phase, so a Berry connection. Okay, so this is tensor network notation. It's maybe the simplest tensor network notation. And then moving toward many body physics, I may be interested in having many such spins. But of course, if I consider just a product of such a state, independent spins, physics is just essentially one-dimensional, zero-dimensional system. So this is the too boring. So we should consider correlated state. And then in my talk, I will focus on the class of state represented by a matrix product state. Okay, we can to be more specific, I'll be focusing on a short-range entangled state or invertible state, which means it's a ground state, unique ground state of some gapped Hamiltonian. And then they can be faithfully represented by a matrix product state in one dimensions. Okay, just to say what to expect. Roughly speaking, this is now a field theory language. I may not use this language, but nevertheless, I want to motivate you and then to sort of give some idea what's going to happen. So in quantum mechanics, I have only one direction, which is time. But now it's a 1D system. So in addition to time, I have a spatial direction. So let's call it sigma. So I have a parameter which depends on adiabatic time t in the Berry phase setting, but now it may depend on t and sigma both. Okay, so that also means if I have a state previously psi which depends on x of t, I have now more complicated object which depends on the configuration of x as a function of t and sigma, like a functional. Okay, so previously I mentioned a Berry phase is just like the coupling in parameter space to the trajectory of particle. Okay, but now I have a two parameter t and sigma. So instead of just considering trajectory, I could think about a surface parameterized by t and sigma. Okay. And then we can also generalize, this is a particle current which couples to, I mean, fictitious particle current, which couples to Berry connection. But natural generalization is to consider sort of a surface current, which has the two indices mu and nu. Okay. So for such current, and therefore it is natural to consider a higher form version of gauge field. So let's call it this B mu nu. So it's a two-form gauge field. And then because of the conservation law, B mu nu has so this coupling B dot J mu nu should have gauge invariance. Okay, this is just to sort of generalizing what we saw in the physics of Berry phase in a very formal way. Okay, it may be possible to pass this direction, but I will now use this just as a motivation. So what we expect is to have is the generalization of Berry phase where connection is two-form. Okay, this is what we may expect. Okay, but to make this expectation more concrete, I will use the tensor network representation of many body state, because in this type of applications, I could sort of abstractly say I may be interested in this type of state, but tensor network representation may give us more a concrete description of such state. Okay, so here's the so the kind of real beginning of the presentation. So I'm interested in short-range entangled or invertible states in one spatial dimensions, and then they can be represented by tensor network, a matrix product state. And then question is there any new kind of Berry phase which can appear because of the many-body nature of this matrix product state? So the higher Berry phase, I think, appears, or at least first mentioned, in the work of Kitaev. And then later, it has been developed a lot by a lot of people, starting, I think, from around here by Kapustin and Spodniko. But there's a lot of works accumulating now. Okay, so I will be able to mention some of them, but perhaps not all of them, unfortunately. But I will focus on the work which are related to tensor network representation of higher Berry phase. Okay. Okay. So here's a quick reminder. I think we saw this actually in this morning, but we are interested in, once again, the short-range entangled state represented by matrix product state. And then I also assume I have a unique ground state. So I'm particularly interested in the class of matrix product states, which are called normal matrix product state, for which the dominant eigenvector of the transfer matrix is unique. Okay. So here's my notation for the transfer matrix, which once again introduced in the Ignacio's lecture this morning. And then I may not be drawing these boxes all times because it takes a lot of time for me to draw. So I may be just using these trivalent vertices to represent this MPS tensor A. Okay. So here is the vertical one, represent the physical indices, and then the horizontal lines represent the virtual space of the matrix product state. And then transfer matrix can act on the vector from the left, like this, or from the right. Okay, and then we are talking about eigenvectors of the matrix product state. But for the type of state we are interested in, we should have a one dominant left and right eigenvectors, and I can normalize this eigenvector to be just one. It's just we can normalize it, or I say we can go to the something called canonical form. Okay. In that case, eigenvector eigenvalue, I normalize it to be one. And I can also make some choice such that right eigenvector is just the identity matrix. This is a vectorial way of saying, I'm calling it vector, but you can think of this as a matrix. So I'm taking it as a matrix. Okay, so in short, I'm interested in normal matrix product state in the so-called right canonical form. In equation, I'm interested in the class of matrix product state which satisfy this condition. Okay. Yeah. So this is just the regular MPS, but following the Berry phase physics, we are now going to discuss the matrix product state depending on parameter. Okay, so that's the next slide. Okay, so now I have a parameter space, okay, as before. So I have a parameter dependent quantum state, but this is now a many body quantum state defined on a one-dimensional lattice. So I have a some matrix product state which depends on parameter x. So I have a of x. And then this type of situation may appear very often. For example, if you are interested in doing variational construction of your state, ground state or excited state, you may be interested in considering parameter-dependent matrix product state. Here, I'm not so much interested in variational calculation, but I'm interested in topological properties of such parameterized matrix product state. As before, I may have to patch the parameter space. And so I put this index alpha to represent this is A in the patch U alpha, and then I have such patches. Okay. So anticipating once again that we may not be able to make a very smooth choice of the matrix product state for the entire parameter space. Okay. So the first thing to consider is to think what could happen if I have these two patches intersect with each other. As before, we did it for the Berry phase as well, but we can also consider similar thing here. So if two patches intersect, I have a two representation of physical state with different matrix product state representation. So A alpha and A beta. And then they represent the same physical state, but they may look different. They may be a different matrices. So now there's the something of fundamental theorem, which was mentioned this morning, but I guess details will come later tomorrow maybe. But if there's if you have a two matrix product state representation, they can represent the same physical state if and only if they are related by this relation. Okay, so A alpha, A beta, they both represent the same physical state, and therefore they must be related in this way, where A beta is conjugated by this G and G dagger, which acts on the barter state. So in the tensor network way of writing it, it may look like this. There is also the phase ambiguity, because quantum state is always ambiguous up to phase, but this part of the ambiguity is related to the physics of regular Berry phase. So I will be mostly just ignoring this part. This part is there, but it's not super interesting. Okay, so if you wish, this is the kind of gauge transformation for a matrix product state, which should play a similar role as the state gauge transformations, which we just discussed in the case of regular Berry phase. Okay, so this is the change we have for the matrix product state representation of 1D quantum many body systems. Okay, so this. Yes, so you can take G to be unitary. Sorry, thank you. Yes, G is a unitary matrix acting on the barter space. Okay. Questions? Yes. Yeah, sorry, I don't really understand the geometric. Sorry. Seems like your tensors are always Yes.
But is that always, are you always take off
Did you say broke diagonalize or no? No. So this is okay. So I was anticipating that I may not be able to make a smooth choice for a of alpha x, a of x, but for the smooth patch, if I make a patch smooth in, small enough within that patch, I can make the matrix products MPS matrix changes smoothly within that patch, and that's the only assumption I'm making. One may think it may not be even possible. That is a
does such gauge information exist if you have more than two auxiliary legs for a tensor?
more than two auxiliary legs. You mean more legs here?
Yeah.
I'm thinking combining them to be one. Yeah. Okay, so maybe I didn't answer the previous question correctly, but perhaps I can back up later. Maybe you have a question? Yes.
Does this transformation preserve the right canonical form?
Yes, it preserves. So that is the actually the condition I impose. So that's why I can take G to be unitary. Other questions? Can I say that again? Is there a notion of covariant derivative or minimal coupling? Covariant derivative. So this is supposed to be the minimal coupling. Although I think I'm not writing like a matter field explicitly. So yeah, for example, I'm using kind of single particle description, but this should really be like a minimal coupling of strings. Yes. Other question? Yeah, use the proof.
By using IPS, I would consider it here only one of them.
Yeah, I will talk about higher dimensions later. Here, for now, one dimensions. The questions? Yes, I will present examples later. So in 0D, the simplest would be S2 or T2. We are going to see the example where M is S3, and then it is defined with the one-dimensional parameter space is S3, physical space is 1D. We are going to see such examples. Yes. Other questions? Okay, good. Okay. So we can also think about what happens if I have a triple intersection. So parties can meet or intersect this way. So then we have now a triple intersection. Okay. So now we have a three MPS to think about: A alpha, A beta, A gamma, and there's also transition functions: G alpha, beta, beta gamma, gamma delta. Oh, sorry, gamma alpha, relating these three MPS. But before discussing MPS, let's just discuss the triple intersection for the regular Berry phase. So for the regular Berry phase, we also had the transition function or gauge transformation. I'm using exponential form, phi alpha beta, phi beta gamma, phi gamma alpha. And then if I have three intersections, we can derive the relation among these transition functions. And it simply follows from this argument. So to go from phi alpha to phi gamma, I can consider a direct gauge transformation between alpha and gamma. So there's the transition function e to I phi alpha gamma. But you could do this in an indirect way to go from phi alpha to psi beta first. And then you can also do the next gauge transformation from psi beta to psi gamma. And then this should be consistent. Okay? So that's consistency states that this must hold. So this is something called co-cycle condition. So this is the regular case. Okay? But now we can discuss how this can be modified if I have an NPS, matrix product state gauge transformation, which is like this. Okay, so now let's see the effect of triple intersection. So we basically repeat this argument. So I first go from A alpha to E beta, and then from A beta to A gamma. So that's one way to relate A alpha and A gamma. But you could also do it in a direct way to go from A alpha to A gamma directly by using this transition function G alpha gamma. We compare these two expressions, and then we may get the consistency condition, which is almost just like as before, except because G acts as a conjugation, there's a U1 phase ambiguity. Okay? So therefore, G alpha beta G beta gamma, which should be almost like G alpha gamma, but it can have a U1 phase. So this is the main change from the previous case. So previous case, this part somehow should just like this exactly. But now this condition holds up to this U1 phase factor, which I'm just writing as a C alpha beta gamma. So this is a new thing which appears in the NPS gauge transformations, which wasn't possible in the previous one because gauge transformation is associated to zero-dimensional single particle. But A is somehow which represents not just a particle. If it is a product state, it's really like a particle, but it represents one-dimensional system, which is like extended, somewhat more extended object. Okay. So formally, we can think about this C alpha beta gamma is defined for each triple intersection. And then basically following the what we saw in the Berry phase. So for the case of regular Berry phase, phi alpha beta or e to phi alpha beta defines eventually the second cohomology group. But now this one has one more index, and therefore it defines a higher cohomology group, H3 of the manifold. And then that is consistent with what we expected. So it is the higher form connection and then also higher form curvature. Although here I'm using the description in terms of transition functions. Okay, so as I said earlier, there may be two ways to think about regular Chern number or classification of parameterized quantum state. One in terms of the curvature and the other in terms of transition function. And here I'm using the kind of transition function language, but this is the generalization we got. Okay. Question, yes. This phase factor. Yeah, so this phase factor is the regular U1 gauge transformation. So I'm just assuming there's no interesting Berry phase, regular Berry phase. So I'm just ignoring it, but you can keep track of it. So yeah, one reason to remove is that this is not interesting, but the other reason is that this may, formally, it may look diverging because each tensor gives rise to E to I chi phase. If you consider thermodynamically large phase, a large system, this phase kind of accumulates. Because this is like coming from each side separately, but this is intrinsically more 1D, so this one does not diverge. Okay, but anyway, I'm just ignoring it. Thank you for the question. Okay, so here's the kind of main part of my talk. So now remember for the work of Wu and Yan, so what they did in effect is to relate the physical gauge transformation of the wave function and the transition function in the mathematical language, or this wave function overlap between different patches, which extract, which identified with this transition function. So once we have this dictionary, we can sort of discuss. We have a kind of dictionary between physical way of thinking about it, and then just math literature, right? So following the similar spirit, we may be interested in what would be the physical in the quote sense maybe, but what is the physics which is related to this U1 phase C alpha beta gamma. So I'm trying to kind of repeat the Wu Yan's thinking, but for in the context of higher Berry phase. Okay, so since there are three patches involved, alpha, beta, gamma, it may be natural to consider some sort of wave function overlap defined for three wave functions, where three wave functions come from three different patches, U alpha and U beta, U gamma. And then this is what we guessed, and it turns out to work in a very nice way. So this is like a inner product, but now defined for three quantum states. So regular inner product may look like this. So I have one quantum state, and there's another quantum state, and they just contract. So that's a regular inner product. So it takes two quantum states, and then it assigns one complex number. So that's an inner product. But now we need a generalized version of the inner product defined for three quantum state. And then this is the generalization we propose. So we have a three MPS, but we bipartition each MPS into two regions, let's say left and right regions, and then we contract them in this way. So of course, this is the inner product possible because it's a one-dimensional many-body systems, because in 0 dimension, there's no kind of flexibility to define such inner product. Okay, so how does this work? So let me first review the regular inner product. So regular inner product, I define this way, but I'm interested in many-body quantum systems in which I have infinitely many degrees of freedom. So I want to take the thermodynamic limit. Yes, question? So bipartitioning here is just a kind of bar chart. I just call this region part A, this region part B.
Right. You change which regions, which like you add like that change.
Yeah. So I'm going to define this such that in the thermodynamic limit, the way we bipartition does not matter. Yeah. So yeah, there's maybe once again the chicken and egg problem, but in the thermodynamic limit, how you bipartition would not matter or should not matter, because in the thermodynamic limit, you have infinitely many left spins and infinitely many right spins. So that's the limit we are going to talk about. Okay, other questions? Yes. Yes, great. So we are going to take a thermodynamic limit in the translational invariant systems. Thank you. Okay, so let's first quickly review how we compute inner product. So inner product may look like this. However, inner product should be a number, but to make a number out of these tensor network contractions, we have to deal with these dangling bonds. Otherwise, it's not the scalar yet. Okay. The second question is that I want to make I want to take a thermodynamic limit. So in the picture, I have only 5 bonds, but I want to take the limit where the number of vertical bonds are infinite. So we do this by using the transfer matrix formalism, which was once again mentioned in this morning. So each vertical bond and these tensors, it defines transfer matrix. So you can consider this inner product calculation as multiplying many transfer matrix. So Ta to power L is appearing here, and then I'm going to make L large. Okay. In the thermodynamic limit, only the dominant eigenvector should survive. So anticipating this, I kind of cap off these regions, these dangling bonds, by using dominant right and left eigenvector. So I take this as a definition of the inner product in the thermodynamic limit. And then in the thermodynamic limit, I multiply TA to power L many times. I mean, I can put any state here, any, some linear superposition of eigenvectors. But in the end, as I multiply TA many times, only the dominant one remains anyway. So this is, in the end, this is what we need to compute in taking L large. But TA acting on right eigenvector, it just reproduces itself. So we can just take this away. Okay? So in the end, this will be the inner product of left and right eigenvectors. And then, yeah, usually we normalize to be 1. Okay? For the just a state normalization. And then we could do the same thing for the triple inner product. So sorry, this is once again handwritten, but I have a these triple intersections. But I take the thermodynamic limit where number of these bonds are infinite here in this direction, and this direction. And then for each leg, I can apply transfer matrix formalism. So we in the end, only the dominant eigenvectors should survive. So it is kind of convenient to rewrite this network in this way. So let's see. This part, sorry, sorry. This part I'm deforming it to this part. This part is this part. This part is this part, such that sense of left and right is obvious. Okay, this way maybe it's pictorially more pleasing, but in the actual calculation, it's a matrix calculation. So I want to make which one is left and which one is right explicit. And then I have just multiply transfer matrix many times. Only difference from the regular inner product is that there's a branching. Okay, there's a branching. But otherwise, it's just a very similar calculation. So in the end, this inner product reduces to, once again, something like an inner product of left and right eigenvectors. But in this case, now I have 2 right eigenvectors and 1 left eigenvector. But anyway, the thermodynamic limit we can take in a way very similar to the regular inner product. So as we follow this calculation, we check that we can check that this triple inner product extract this U1 phase C alpha beta gamma. Okay, so this is very analogous to this regular inner product between different patches which extract the gauge transformation. Okay. Okay. Yeah. Question.
So it seems like you could have, tried it the other way that you had 2.
Yes, that's right. So yeah, so we played with these degrees of freedom. In the end, we found this may be the best choice for various reasons. For example, if you put 2 left eigenvectors by bending this to the left, you get a product of 2 left eigenvectors, which is not normalized. So if in this way, if I normalize 2 regular inner product, this is automatically normalized. We found it's a bit nice. There's also kind of a I can talk offline, but you can think of this as like just like a matrix multiplication, which I may mention later. So you can think about this part is like a big matrix where I have yeah. So if I write this way, this defines a particular state in a tensor network representation, but you can also bend this state. If I write this way. So if I write this way, this is like operator which take input and then output. So this convention turns out to be consistent with the regular matrix multiplication, if it makes sense. I think I can perhaps mention this a bit more later. Other questions? Yes, question?
So this particular growth of the triple inner product seems to be a feature of the fact that you work with right canonical
Yes, yes, that's right, that's right. You can.
Can you make some general statement about what if I don't work with left or right, but some sort of mixed in between, or like is it then just very, very hard to define?
That's a very interesting question. So we did once again try various kind of conventions. I don't have a systematic way to understand them all. This is the one we use. And then there's another paper by other group which uses slightly different notation. So we think this is very nice, but this may be, there may be other choice may be possible. I think it's noteworthy though that there's something called mixed gauge where we mix left and right gauge, and it also has a very nice feature. So here I'm using right canonical gauge, but we can also use mixed gauge, which is actually also nice. So yeah, it's at this stage it's a bit tough question to say which one is the best, but there may be some room for discussion, I guess. Other questions? Okay, let's see, 20 more minutes. Okay, yeah. So far I focused on the description using transition functions like Wu and Yan's description of magnetic monopole, but we kind of doing the many body version of Wu and Yan, or MPS version of Wu and Yan. But how about curvature and the connection? That was the first point of view I mentioned in the review of Berry phase. So there's several works starting from this work, Kapustin and Spodenico. There are various approaches. I think all approaches are very interesting, but I will focus here today for the tensor network approach. So in terms of tensor network, MPS, we can also write down curvature and the connection. So this is the kind of summary of the result. So now using the MPS tensor, which depends on parameter, like in the regular Berry connection formula, you may be interested in writing Berry connection using a derivative of wave function. In this case, we may be interested in writing down higher Berry connection using the derivative of MPS tensors. And then to make a long story short, this is the formula we came up with. So these are written in these papers. I think from our perspective, we started from the triple inner product, and then like in the regular Berry phase, we make instead of taking 3 physically equivalent state in different gauge, we just take 3 states which are slightly at different positions in the parameter space. We did this type of calculation. In the end, we summarize our result this way. This paper took slightly different route, which is kind of make use of the Kitaev's idea and similarly Kapustin, Spodenico's idea, but the results are the same as far as I understand. So we have a tensor network written in terms of parameter dependent tensor A. And then there's also the parameter dependent left and right eigenvectors. So the two-form connection is given in terms of this derivative expression. We have an infinite sum this way, but we can also sum this, perform this summation explicitly. I don't know, in the Feynman diagram language, this is like a ladder diagram summation. But anyway, we can write down the expression for the Berry connection. This paper also discussed the similar formula for the curvature. Okay. Okay, sorry. The number of vertical lines, sorry. So I have many vertical bonds. And then, yeah, so it's summed here. Sorry, so I did not mention that.
The basic first state had this bond dimension. So this is all in the limit of infinite bond dimension.
Oh, that's a very good question. So for the simplicity of the presentation, I pretended it is finite constant dimension over all m. As it turns out, if you want to express very interesting family of state, bond dimension must change as a function of x, or as you go from one patch to another. We get slightly more complicated formula, but essentially the same argument force. So I can tell you a bit more if you're interested, but it's a very important point. But in these presentations, I'm just pretended everything, all these bond dimensions is finite and constant. Other questions? Yes? Yes, that's right. So I could. So this is, I'm because I'm now taking the kind of regular Berry phase approach. I'm just staying within one patch, but I'm interested in 3 different points within each patch. So yeah, that if necessary, I can even remove this alpha. But I'm assuming I have a smooth MPS descriptions at least for some region in M, and then I take a derivative. Okay. The questions? Yeah. Okay. So I think I want to present some applications because so for the presentation maybe a bit too formal. So I want to use this particular example discussed in a very nice way in this paper. So this is the one-dimensional spin one-half quantum systems, which depends on parameters W1, 2, 3, 4. Sorry, maybe Hamiltonian itself may be a bit too small, but details are not very important. So it's just I have a site-dependent Zeeman field, which is 3 component. It's like a staggered Zeeman field. And there's also the parameter-dependent bond, which we split into the even bonds for the and the odd bonds connecting these sites and these sites. Okay. So this is the let's say as I change the force parameter W4, the bond strengths start from here, where only the, let's say, I forgot which one, but let's say only the even part of the Hamiltonian is active, this part is 0. And as I change this parameter W4, eventually I switch the dimerization pattern through this particular point where bond bond is just 0. Okay? The previous formula, this is exactly solvable model, so we can find the exact MPS representation analytically, and then utilizing the previous formula, we can check explicitly that two-form connection is given this way, and then the quantization of the two-form connection we can also check. I think it's even more interesting because they're oh, sorry. So W is I'm sorry. W is this parameter W. I'm using the radial coordinate. So the force component is t, but there's the other directions, phi and theta, which did not show up here. But anyway, this depends on the direction of the W vector. The questions? Okay. So I think very interesting development is that we can study Berry connection, Berry curvature, even for non-solvable models. So I want to introduce these two nice works. In this paper, the slight modification of this Hamiltonian. This Hamiltonian, we can solve this by hand, but you can perturb this model such that it is not possible to get analytical solution anymore. But you can still do, let's say, DMRG calculations to find the tensor network MPS representation. So this work presents the, in addition to the analytical result, it also demonstrates that higher Berry phase calculation can be implemented using the tensor network DMRG calculations. So the topological invariant is nicely quantized within numerical errors. And then this is how the integrand, Berry curvature, evolves as you change some parameter alpha. I also want to introduce this paper, which took slightly different approach. This paper did not use this formula itself, but they triangulate the parameter space, and then they just basically they compute the triple inner product for very small triangles, and they just sum up. This is analogous to the similar calculation for the regular Berry phase, where you can triangulate, or you can split your parameter space into small squares. And then each link, you can just compute the wave function overlap without taking derivative. That actually works very well. So this one also, such approach also works for the higher Berry phase. So, so it started to be possible to evaluate the higher Berry phase for very broad class of many body quantum systems, not just analytically, but beyond numerics. So hopefully more applications appear in the future. Okay, so how much time do I have? Like 10 more minutes? Yeah, okay, good. So I just want to conclude briefly by briefly mentioning possible higher dimensional generalization. It is a bit more complicated, and then it has to be a bit schematic. So I'm sorry for this, but I'm happy to talk later for more details. So, so what we would do, so now we have a two-dimensional system, and then possibly we could have two-dimensional tensor network representing some correlated state, short-range entangled state, for example, PEPs, okay? So in one dimension, we had the triple inner product with 3 states, and then we now want to have a generalization, and the generalization naturally involves 4 quantum states. And then previously, I had to have a bipartition of 1D system, but we could now a tripartition 2-dimensional space into 3 regions A, B, C. So this is the 2-dimensional plane, let's say, and then physical space, not the parameter space. And I tripartition this physical space into 3 regions A, B, and C. And then we can contract these PEPs by using this tripartitioning. Unlike 1D, it's a bit more difficult to draw. If I draw, it looks like this, but I think I prefer to use simplified diagram here. So let's review triple inner product using this simplified notation. So in defining triple inner product, I had to bipartition my 1D space into 2 regions, left and right. So schematically, I can write this way. So that's what I kind of mentioned previously. This wave function psi ij can be thought of as like a matrix. I mean, that's also common in the language when we do Schmidt decompositions and so on and so forth. But then I have I can think about the wave function as a 2-index object. So I have a psi alpha, which has 2 index, one for region A and the other for region B. And the triple inner product can be summarized in this way. And the direction means which one is conjugate and which one is unconjugated. So this is a concise way to summarize triple inner product. Regular inner product just looks like a line because I don't have to do partitioning. I just connect these 2 states. And following this line in 1 high dimensions, I make a tripartition for 2D space. So schematically, my state looks like this. So now a state is a 3-index object, and I can think about contracting them in this way. A question, yes? That's a very good question. So, so this may break lattice symmetry, yes. So for example, it may make sense to consider quadruple partitioning if we want to preserve C4 symmetry, for example. So I think for the application, it may be important to consider lattice symmetries, yes. No, so yes. So I actually, sorry, I did not write down the tensor network itself, but this is just a spatial region. So microscopically, I may have many four-leg tensors, which may be consistent with C4 symmetry, but entanglement boundary, sorry, this partitioning boundary may break C4 symmetry. So yeah, let's say if I want to keep C4 symmetry, I use four virtual legs, and then I also make the partitioning which respect to C4 symmetry, for example. So yeah, sorry, I didn't write tensors explicit. But here, microscopically, the PEPS tensor can't be four legs, three four-leg tensors. The question, yes? Yes, it's go to one somehow kind of one higher. Yes, so that is the, yeah, so I'm trying to be very schematic, unfortunately, but then for each this interface where two states meet, once again, I have to deal with the dangling bonds, which showed up in the triple inner product, but now it's an extended region, and I expect there's some one-dimensional operator, let's say MPO or matrix product unitary, which cap off this region. So this is just analogous to 1D case. But additionally, there's now this sort of vertex where there's four states meet and three interfaces meet. So we need additional consideration for such a vertex region. So we need to define new object, which has a three-leg object, which connect these three matrix product operators, which are used to cap off this region. So yeah, so anyway, I cannot give a very detailed description, unfortunately, but there's some way to generalize it. And then in the end, so in the 1+1D case, I had a network of eigenvectors of transfer matrix, and similarly, we can define a 3D network of these three-leg tensors. That we can also think about, think as a generalization of this object. So this is the higher Berry phase or quadruple inner product formula for the higher Berry phase in one higher dimensions. Okay, and then I think I have to basically end here. But let me first summarize. So we developed the higher Berry phase formulation for the higher Berry phase using a wave function overlap or multi-wave function overlap. So there's various things I was not able to mention, unfortunately. But yeah, so this is the CBA's question, which is actually physically very important, but I had to skip some details. Another maybe interesting math fact is that the regular case, the mathematical framework for the Berry phase is the principal fiber bundle or a complex line bundle. And then there's a similar object, which is the kind of mathematical framework for higher Berry phase. It's called jar, but I guess for my talk today, we don't have to get into that details. And then there's also kind of more physical perspective, such as the more applications, including application to symmetry protected topological phases. And then regular topological phases without parameter has a bulk boundary correspondence. And there's the similar, there's a version of bulk boundary correspondence for the parameterized family of quantum many-body state, which has been discussed here. And then I think with that, I think I have to end. So thank you very much for your attention.
We have time for a few questions. Maybe I'll start in the back. Yeah, here. Yes. Okay. Thanks for the talk. So I just have one question. So if I consider instead the GAZ state, right? So I don't have normal tensors. So what would I change here?
You want to have a
Yeah,
you
you
want
assume
normal MPS, but
yeah, like non-normal MPS, like GAZ.
the interesting question. So yeah, so in that case, yeah, so we may not define a amplitude because, yeah, so this is not the right picture, but yeah, we may have some freedom because of the degeneracy. Okay, which paper? Yeah, so, okay, so short answer is I haven't thought about this, but we may, this defines some, assign some number, but we may have to define set of numbers or something like that. But that yeah, I haven't thought about it. That may be an interesting question.
And maybe it was slide 20 or 19, you summarized all of your results and you had this H3. Was that like the field strength?
Oh yeah, sorry, maybe I did not mention that. So sorry, H3 is the three-form field strength, which is dBA, sorry, dB. Sorry, I forgot to mention that. Thank you for, so that's why I have a one more derivative, yes.
A here, like the one form for the normal Berry connection?
So yeah, in the normal case, this is a one form, and this is A, and this is F, and the two form, and everything is now one higher form.
Gerbs.
Yes.
Where normally this be.
Yeah. So this is yeah. So in addition, there's also the one form connection. Sorry, but I'm not writing it here. But we also have a formula for the one form connection. That is actually very simple. So I did not write it, but that is part of the dictionary. Yes. Yeah.
What's an example of pattern space where the H3 depends on
H3 depends on the one form connection. I see. So I don't know such examples, but yeah, that may be interesting to think about. Yeah, I didn't have any example. Yeah.
So if you have a lab of more than 3 patches, let's say 4 patches, then would you get additional constraints?
That's right. So I think something I didn't really mention that is that here I consider 3 patches, and if I consider 4 patches, I get once again cost cycle condition. So for the regular case, this is a condition. We get the kind of one higher version of these conditions, so that this is sort of kind of closed in that sense. So we have to also go study coordinate intersections to check that, which I skipped, but so that similar thing happens. So even for the 2 dimensions, you also check higher intersections as well.
And the way that makes benefits sort of literature numbers into the edge space. So is there some data and give it the higher space that you're talking
Yeah, so that may be related to maybe this topic. Yeah, so there's similar, or not similar, maybe similar is maybe not correct word, but there's a version of boundary correspondence for the parameterized family. So yeah, I don't think I have enough knowledge to say about it, but yeah, I encourage you to look at these papers, which discusses the kind of flow of Berry curvature along the interface as you change parameters. Yes. Yes.
So like it seems like you glue this different MPS on like a one-dimensional line, but this MPS, they are the two-dimensional systems. So do you somehow like unravel the two-dimensional maps into like a string?
So here I'm trying to, yeah, I'm pretty sure this drawing is not good enough. Yeah, um, I have basically four sheets, each represent 2D peps. I don't consider 1D kind of unwrapping, but just consider 2D sheet. I have a 4 such sheet. And then, so you could imagine I have a 4 copies of this sheet. And then I have to say region A of first wave function is glued to the region, I don't remember exactly, but let's say region B of second wave function, so on and so forth. So that's I try to draw that here, but I'm pretty sure this is kind of confusing. So diagrammatically, I'd write this way.
Is any connected to properties of defects or higher dimensional defects?
Oh, I'm glad you asked. So because it's also related to maybe some of the topics in this. Okay, I'm not sure this is what you want to see, but what happens is these like a defects, right? As you patch and you glue, you have a domain wall between different wave functions. And then through some bulk boundary correspondence, which may not be entirely necessary, but you can sort of express inner product of 2D wave functions using the language of edge conformal field theory. And then, as it turns out, quadrat inner product is related to the CFT partition function with defects. So this is kind of particular connection we made. And then, but perhaps more broadly, I think it's related to the idea of making domain wall. So if you look at this this region, so I try to draw this way. But for example, you can think about this part as a physical state, starting from beta patch to alpha patch. So there's a domain wall here. Okay, so you're kind of gluing 3 domain walls together. So that is the triple inner product. So that is also related to the previous comment about mixed gauge MPS. So I think you can also take the point of view that you are dealing with quantum state with defects. That is related to the higher Berry phase. Yeah, I can discuss a bit more later.
Actually, maybe I don't know, quantum then. Do you have a formula for the phase strength or for H for continuum field theory?
Continuum field theory. Yes. So I don't have a formula. I don't have a formula. So yeah, maybe we can develop along this line, and then we don't have a formula. Somebody else may have thought about it, but yeah, we don't have a formula. Yeah, so maybe it's, yeah, we can discuss this later, but I don't have example. It may be possible, but okay, you studied this, right? So and then, yeah, we didn't get any results, so I guess no, but yeah, okay, but it's good to, I think, have a further thought.
Have a non-moving general what happens to the variable?
Yeah, so that's a very good question, of course. We don't have that for now in this simplest case. It may be possible, but we sort of expect it's much more complicated. I mean, this is a higher form symmetry. Higher form symmetry is usually formulated for the abelian case most easily. So yeah, you could consider non-abelian two-form gauge field possibly, but I think it's more difficult. But yeah, short answer is we have not thought about it. it's fundamentally difficult, I guess. Yes.
Okay, no more questions. I have a few announcements, but before I get to that, let's first thank Shinsei for a great